So looking at our last page, we're going to use this graph of f of x to help us evaluate these different integral values. So for the first one, we're going to try to figure out the area under the f of x graph from 0 to 3. So if I kind of shade in that area, I want to start at 0, end at 3, here's my curve, and I want everything underneath this curve to the x-axis. So I'm going to try to figure out what all of this area calculation would be. And since we don't have an equation to physically work backwards from, maybe we can use kind of similar shapes or geometric shapes on the graph to help us figure out the area. For instance, in this section here, I have a quarter circle, and then underneath the quarter circle, I have this rectangle, and on the end of the rectangle, I have this triangle. So you can kind of break up the area into geometric shapes to help you figure out the overall area using those geometric shape area formulas. So for my semicircle, quarter circle, I need 1/4 pi times the radius squared. So here's my center, I go out to the edge, and that would be a distance of 2. Then I'm going to add the area of this rectangle, which has a base of 2 and a height of 1. And then I'll add the area of this triangle on the end. So that'd be 1/2, the base is 1, and the height is 1. So altogether, we have 2 squared, which is 4, times a quarter is 1. So I'm just going to be left with pi. Then we have plus 2 plus 1/2. So it seems like our overall area under the curve from 0 to 3 is pi plus 2.5. So notice how we can do that without a calculator. If you were more comfortable with typing this in and get a decimal value, that's perfectly fine, but this is a more exact representation than just a rounded decimal. So for the next one, this time we're going to go from 0 to 4. So actually, if we thought about highlighting it, we would still highlight all of the area that we had previously, but now we also want to include this little triangle area from 3 to 4. So if we think about a property, we could actually rewrite this as the area from 0 to 3, and then we'll add the area from 3 to 4. And by doing this, notice how we already know this value because we actually did that up top. So we can just rewrite this as pi plus 2.5. And now we want to add the area that's left over, so from this 3 to 4 section. So notice how this section is a triangle, so we're going to need 1/2 times the base of 1 times the height of 1, but notice how this area is strictly underneath the x-axis, so we need to be sure to show that concept by putting in a negative value. So even though you're adding an area, you're actually adding a negative result or a negative amount, so that's going to be the same thing as subtracting. So if we take pi plus 2.5 minus 0.5, we're just going to be left with pi plus 2. Alright, let's check out the next one. What is the area under the curve from -3 to +3? So I'm going to erase that little section from before, and this time though I want to start at -3, so all the way over here. So I'm going to shade in all of this. Okay, now you could go through the whole area calculation again by breaking it up into geometric shapes, but notice how this is when properties are definitely going to be useful for us, because if you look at the shape or the type of graph that we have here, f of x is even, because if you were to fold the left side over to the right side and make the crease on the y-axis, everything would match up perfectly. Okay, so folded over, it would kind of land on itself. So we do have a property related to even functions because what's on the left is the same as what's on the right. So instead of writing an integral from -3 to +3, I can write an integral from 0 to 3, which is basically half of the area I want. And if I want to include the other half, I'll simply double it. So this is useful because we already know, again, what the area from 0 to 3 was. We calculated that at the very beginning. So if I just double this area, I'll get 2 pi plus 5. Okay, so again, using properties of these integrals, it's going to help us make these area calculations a little bit simpler. So we're just going to go ahead and use them to our advantage when we can. All right, the bottom two are going to be slightly different. In this case, we're not necessarily using a property of integrals. It's more of a definition per se. So if capital F, we're going to assume, or they actually tell us, where capital F is the antiderivative of f of x. So if we were to work backwards from the f of x equation, which we actually don't have, but if we were to work backwards, we know some point value from that antiderivative. So if we were to plug in 0 in the antiderivative, we would get 5. And using that information, we wanted to somehow figure out what is the antiderivative value at 3. So if we think about what we're doing here, if we are using an antiderivative, that means we're working backwards. So if I were to write the integral of f of x dx, we know if we work backwards from f of x, this should represent the antiderivative. And typically you could write plus c there because maybe we don't know the bounds, but we're actually going to use some of the information to help us figure out what the bounds should be. And if you look at the previous examples, typically the bounds represent the x value that you want to start the area calculation and end the area calculation. So if we look at the information that we know or what we're trying to find, notice how this x value is 0 and this x value is 3. So we're going to strategically choose those as the bounds on the integral. So if I use 0 and 3 on the integral, I should also write them on the bracket when I work backwards to find that antiderivative. Okay, so if we actually write out what we have here, the area under the f of x graph from 0 to 3 is exactly the same as the antiderivative value at 3 minus the antiderivative value at 0. Okay, if we use that fundamental theorem of calculus doing that top minus bottom property. So notice again how we already know what the area under the f of x graph is. We said that was pi plus 2.5. And for this question, our ultimate goal is to figure out f of 3, or capital F of 3, so we're going to leave that the same. But we do know what f of 0 is. They told us that was 5. So putting the little pieces together, kind of in a mathematical puzzle, we can solve for this f of 3 by simply adding the 5 over. So this would be pi plus 7.5. Okay. This type of question I know is a little bit different from the ones that we've seen in the past. We will definitely talk about this setup or what this is actually telling us in a future course, but for now I think it's a good example that relates the area under the curve that we can find either based off of a graph or an equation and how that is connected to the antiderivative of a function. All right, let's try the next one. So very similar. If capital F of negative 2 is negative 2, what's the value of f of positive 2? Again, f is the antiderivative. So if we're finding or using an antiderivative, that most likely means we were working backwards. So if we work backwards from f of x, that would give us an antiderivative of capital F. Okay, that's what they mean by the antiderivative of f of x. Knowing some of the point values or information they give us, we can see how we have an x value of negative 2 and an x value of positive 2. So again, we'll strategically use those as our bounds, which therefore will be also used on our bracket when we evaluate the antiderivative. So this statement, according to the first fundamental theorem of calculus, is telling us that the area under the f of x graph from negative 2 to positive 2 is the same as the antiderivative at 2 minus the antiderivative at negative 2. Now, this is not one of the area calculations that we've done in a previous problem, so we might actually have to calculate this one out. So if I shade it, I'm going to go from negative 2 to positive 2 and everything in there. So it looks like you can use the symmetry concept because it is even after all, and you're going on the same to the left as you are to the right, but maybe you just want to calculate everything straightforwardly. So it seems like I have a semicircle as well as a rectangle. So for my semicircle, my area would be 1/2 pi. The radius we already said previously was 2, and I'll square that. And I'll add the area of the rectangle, which has a base of 4 and a height of 1. All right, so that's the area under the f of x graph. On the right-hand side, we're going to use some antiderivative information. We're trying to figure out f of 2, but we're going to subtract the f of -2 values. So if we subtract -2, that's actually the same as adding 2. So solving for f of 2, let's see, this would be 2 pi plus 4. And if I subtract the 2 over, I'll have 2 pi plus 2.